Welcome to the next video in the real analysis video series, and in this video we will be proving the claim that we stated in the previous, at the end of the previous video, this exercise, to show that if a set has a maximum, then that maximum must be unique. Okay, let's assume that X is a set of numbers which has a maximum, and let's call that maximum M. Now, we're trying to prove that M is the unique maximum of X, and so, as we often do when proving uniqueness claims, we will take some other thing that also satisfies the condition or the property. In this case, that means let's take some other thing which is a maximum for X. And then what we want to do is prove that M and N are equal. That's our goal, right? We take any other thing and show that it was actually equal to our first thing all along, so there was really only ever one thing. That's how you prove uniqueness. Okay, let N be any other maximum, and what that just means by definition is that if you take any element out of the set X, then little x is less than or equal to my maximum M, but also less than or equal to my maximum N. Now, we know by definition of a maximum that the maximum M and also the maximum N, they are both elements of my set X, and therefore, because they are in X, they can be taken to be one of the examples of this little x, right? Because this is true for all elements of my set, then I can, make this statement, setting X equal to both M and N at will, right, so to speak. So if we then take this version and we set X equal to M, we get this. If we take this version and set X equal to N, then we get this. And then when you put these two together, you get equality by the linear ordering axiom. And it's probably a good thing to note right now that the technique used above proving two different equalities to therefore infer an equality. This is almost like the main method, or you just see this in analysis. It is so distinctive and characteristic of the study of analysis that this is something that you do all the time in analysis, and it's something you do very rarely in other mathematics contexts, especially like algebra and stuff like that, that this is really, worth paying attention to and looking out for, right, in future proofs when you're trying to think about how to prove some two things are equal, especially two numbers are equal. It's always a good idea to think about whether or not it is easier to prove one or the other inequality. And that could be just a good, and if it is, right, if it is easier to prove inequalities, then try to get these two inequalities, and that'll get you the equality. So, okay, it is important to note that some sets do not have a maximum or a minimum, and by the way, that is true if the set is unbounded. It just goes off to infinity in one direction or the other or both. But it is also true for certain fine or bounded sets, right? So take, for instance, the set of real numbers between 0 and 1 strictly, so that 0 is not in the set, and therefore it is not a minimum of the set. However, in some sense, we still, right, 0 somehow still characterizes the lower end of the set the way that you would hope that the minimum does, but it's just technically not the minimum. So we would like to somehow define, right, like if we can't call it a minimum, because it's, being a minimum of a set, being an element of the set is, we have seen in a couple theorems already, a fairly useful fact, which would not be usable here. So we can't just change what we mean by minimum, right? We can't say like, we should say that 0 is still the minimum of the set, because it's clearly kind of like what we mean or what we're interested in when we think about a minimum. Well, you can't really do that because, being an element of the set seems to give you useful properties that would not hold here. So we can't just say that, we can't just change our definition of a minimum so that we allow things to be outside the set and still be a minimum. So what we do instead is we just come up with another definition that recognizes, like that 0 is somehow special, but it's still not the least element of the set, right? And of course, everything that I have just said for the left end, the lower end of the set, holds just as well for the upper end of the set. And so what we're going to do is we're going to define a new concept, the infimum and supremum, right? So the infimum of this interval 0 to 1 exclusive is going to turn out to be 0 when we define it appropriately, and the supremum of the same set is going to be 1. Okay, let's define it. So let X be a non-empty set of numbers with an upper bound. Let's say that U is actually the set of all of the upper bounds of X. In that case, we say that the supremum of X is the minimum of U if this minimum exists. So let's apply this idea again to the interval from 0 to 1. And if you think about the set of all of its upper bounds, right, its set U, the set of all of its upper bounds, is the set 1 to infinity, right? All of those numbers are upper bounds of this interval. And then the minimum of that set, the minimum of U, is the least element, which is 1. So that confirms, right? You can see applied to this particular instance, we knew that we wanted the supremum to be 1, and it turned out to be 1. So it seems like a well-constructed definition for what we wanted. Of course, there's the notation that we denote the supremum of a set when it exists by this sup x notation, and it is also often called the least upper bound, which I think from what we've described already makes total sense. Of course, we can repeat all of this for the infimum. Here you would take the set of lower bounds and then take the max over that. And we often call this the greatest lower bound. Okay, these definitions require U and L to have a minimum and a maximum, but we've already seen earlier that some sets do not have a minimum or a maximum. And so what happens if these sets don't have a minimum or a maximum? And I want to emphasize that this is not just pretending to worry or something like that, that in fact this can happen. Consider the set of all rational numbers in the interval from 0 to 1. Now here, okay, the concern is not going to happen in this case. Let's see what happens. So what is the set of upper bounds for this set? Well, it somewhat depends, right? Are we taking the upper bounds chosen from the real numbers or the rationals, right? I mean, especially because I said that I'm taking my number set from the rationals, it is very reasonable to think that the set of upper bounds should likewise be chosen from the rationals. Typically, if you're going to live in the rationals, then you're really going to live in the world of the rational numbers. So if our upper bounds are taken from the reals, however, then the number root 2 is going to be in the set of upper bounds. If we are taking our, because that's a real number that is not rational, which we'll talk more about later. But if we take our upper bounds only from the rational numbers, then this would not be true. Okay, but so far there's no real issue. But now let's get to a different example. Let's consider this example. This is the set of all, I think I have a mistake there. So that should just be a plain 2. Anyway, so let's take the set of all rational numbers whose square is less than 2. And clearly there are rational numbers in this set. 0 is an instance, 1 is an instance, -1 is, these are all elements of this set X. They're all rational numbers. And in fact, you can get closer and closer. I think 1.1 would also count. 1.2, I think counts. Pretty sure that counts. 1.3 3. Anyway, yeah, what I think like go up to 1.4 or something like that. If you know the decimal expansion of root 2 off the top of your head, then you just get really close to the decimal expansion of root 2. I'm not sure I remember all even more than a couple digits of the decimal expansion of root 2. But in any case, the important thing is that this is a set of rational numbers. And if you think about the set of all upper bounds for this set, now what is the set of all upper bounds for this set? Well, if you're in the real numbers, it's pretty easy. It doesn't take too much work to convince yourself that then the set of all upper bounds is equal to the set containing root 2, because that's right on the edge, and then going up to infinity. But if you're in the rational numbers, then root 2 doesn't exist. So if your set of upper bounds is now chosen from the rational numbers, then the set of upper bounds is more descriptively written as exclusive of root 2 out to infinity, right? Because you couldn't include this. That's not in the rational numbers. So this would be the interval of all rational numbers, which are, in a sense, bigger than root 2. It's a little awkward to kind of talk about, the rational numbers, which are somehow defined in terms of a real number. But, I'm not going to get too lost in the weeds on that issue. The point is just that when you take your rational numbers, right, when you take your set of upper bounds from the rational numbers, your set of upper bounds no longer has a minimum. And then the supremum no longer exists. So that's the important point, right? So it is possible for your set of upper bounds to not have a minimum. It is possible, for the set of lower bounds to not have a maximum. And really, it's not just in this example. This is a pervasive difference between the real numbers and the rational numbers, right? The rational numbers tend to be gappy, that the rational numbers are missing this number, which in a certain kind of sense is like some point on the number line that you would like to have, but it's missing, whereas the real numbers sort of, fill all the gaps. So in that way, when working with the real numbers, you are guaranteed that, for a set that is non-empty bounded above, its supremum will always exist, right? So the fact that this set lacks a supremum when the upper bounds are taken from the rational numbers, that is in a way kind of the fault of the rational numbers, and it is a fault that is fixed by instead using the real numbers. So for that reason, because the real numbers are useful in that sense, that they sort of just guarantee us that the supremum always exists and that we can talk about it and use it, then the real numbers are just a simpler, easier object to work with, and therefore for the rest of this course, we will be using basically, our sets of upper bounds will always come from the real numbers so that we can be guaranteed that for a non-empty set bounded above, the supremum is guaranteed to exist.